Chapter 7b, Residuals and the Regression line. So we've seen the regression line. Now we're going to be able to predict how good are the predictions and how can we measure the error in a prediction. This term residual refers to the error in a prediction. Read through our learning objectives for this activity and our vocabulary here. And take a look at example 1. So here is a graph from Vitruvius comparing the arm span of a man to the height of a man. And you may have heard that some people say the man's or woman's arm span, if you stretch your arms all the way from tip of one fingertip to the other fingertip, is the same or very close to the height. So these measurements are in centimeters. So we're going to see with this line of best fit, how accurate are the predictions. So think about the arm span of 173 centimeters. So notice the scale on the arm span axis here on the x-axis is counting by 2s, whereas the scale of the height on the y-axis is counting by 1 centimeter. So this person who has an arm span of 173 centimeters is going to be right here between 172 and 174 centimeters. And if we come up here, it looks like their observed height is 185 centimeters. So we say that's a error in this distance, the observed value minus the predicted value. This is the residual or the error. And sometimes we draw these bars to show how far the error is from the line. If we look at the man who had an arm span of 196 centimeters, that's out here, and we find the observed height, their observed height is 184 centimeters. And so that is below the line, so this would be a negative error. The observed minus the prediction is going to be a negative value. So now we want to estimate from the least squares regression line what the prediction was. So for the man with the arm span of 173, looks like the prediction is 174 centimeters height. And similarly for the man with the arm span of 196 centimeters, it looks like the height prediction was 191 centimeters here. So obviously our least squares regression line isn't going to be a perfect prediction for every man. So we want to think about how far off they are. So the man with the arm span of 173 centimeters, his observed height is 185 centimeters. So the prediction is an underestimate. So when we calculate the prediction calculation, we want to think about, well, what's the error or the residual? So we say, what's the observed value minus the predicted value? And 185 centimeters minus 174 centimeters, we get a positive 11 centimeter error residual. So if you look back at the graph, this actual observed data point was 11 centimeters above the line of best fit there. Similarly, if we think about the man with the arm span of 196 centimeters, the line was overestimating his height, so the residual is going to be 184 minus 191 centimeters. That's prediction. And so that's a negative residual. So if we look back at the plot, his error bar is below the line, right? Indicating a negative error there. So another example gives us the equation for the predicted speed for a roller coaster. So the predicted speed is 40.31 plus 0.18 times the height, or if you want to translate that, we can say y is the predicted speed and x is the height of the roller coaster, and that's in feet, and the speed is in miles per hour. So this line of best fit was found from this data set of 20 roller coasters, and here's our rate. It's 0.18 miles per hour for each foot in height that the roller coaster increases. So every extra foot, the speed goes up 0.18 miles per hour overall. So we want to look at the table to find the observed speed. So the roller coaster that has a height of 72 feet has an observed speed of 44, and then the roller coaster that has an observed height of 415 has an observed speed of 100 miles per hour. So now let's plug these values into the equation and see what our predictions are. So when the height is 72, we plug this into the equation, 0.18 times 72 plus 40.31. That predicts 53.27. So that's an overestimate from the 44 miles per hour that were actually observed. Similarly, if we plug in 415 into the line of best fit, 0.18 times 415 plus 40.31 gives us 115 miles an hour, also an overestimate. So these predictions are both overestimates. So when we calculate observed minus predicted, we're going to end up with a negative residual. So here for this roller coaster that's 415 feet, the observed speed was 100 miles per hour. We subtract the prediction 115 miles per hour and we get this negative residual. So residuals, same thing as errors. You can use that term interchangeably, and they're going to be positive or negative depending on which side of the line the actual data falls on. So let's look at some different line of best fits to try to figure out which one is actually for sure the best fit. So we're going to look at some different linear models here. So these graphs are all the same scatter plot. They are the backpack weight over here on the y-axis as a percentage of the body weight. So these are percents of the body weight of the student, and these are students in grades 1, 3, 5, and 7. So notice when you look at these four graphs, the points are all the same. The difference is these different lines that they're trying to fit to the point. So the first line here is y equals negative 17.7143 plus 0.4143x. Remember, sometimes we get a negative initial value. It doesn't necessarily make sense that we'd have a student with 0 body weight, so the negative initial value you'd see is kind of outside the purview of our graph. So eyeball fit, which line looks like the best fit? It's hard to tell. Notice line D here is just a flat line, so its equation is just y equals 19.5. It has no slope because it doesn't change. The other graphs all have linear slopes that are positive, so I'll let you try to determine what looks like the line of best fit. So we're going to do some math to try to figure out which choice we think is best. So here is a table filled in with the body weight in column X, the percent of the body weight that the backpack is in column Y, and then our predictions for each of these X values. So for example, if we plug in X equals 34 into line A, this is the percentage it predicts. If we plug X equals 34 into line B, this is the percentage predicted by line B. If we plug X equals 34 pounds into line C, this is the percentage predicted by line C. And then line D is always predicting 19%. So some of the calculations are missing. So for example, take X equals 51 and work back and plug that into each of these four equations for the X values and verify these four calculations I got here for an X value of 51. Similarly, you can verify for an X value of 82 pounds and plug in these four values, or plug X equals 82 into these four equations, and you should get back out these four values. So now, eyeballing the table, what do you think could be the best predicting line? So eyeballing the table, I'd say, is even more difficult than eyeballing the graph. So we need to do some mathematical calculations to really determine which of these lines is the best fit. So we're going to use the residual, or the error, to help make our decision. We want the line with the least amount of error overall. So you can see here is line A again, going through our same scatterplot data. And we have circled the student so the line comes closest. And we have circled the student the line is furthest away. And then for each of these students, we've taken their actual or observed data. Here's the line A predictions. And then we're finding the residual. So you can check if you take the student who weighs 34 pounds, the actual value 9% minus a prediction, which is negative, gives us a value of 12.628. Remember, when we subtract a negative, that changes the sign. You can see also if we say 16 minus 0.5149, here's our error or residual, 15.485. So we're missing a value here for the student who's 62 pounds, so verify 18 minus 7.9723 is 10.0277, and similarly for the student who weighs 119 pounds, you can verify 18 minus the prediction of 31.5874% is negative 13.5874. I didn't make you fill in all the residuals because that would be quite a bit of subtraction, but I do want you to go through the process of checking a couple, because on homework you'll have to find a couple errors or residuals. Similarly, here's line B, and we circled the student who's closest and the student who's furthest away. You can verify that in the residuals, right? If we look over here at the residuals, the closest value is the student who weighs 54 pounds with a residual of 0.6302, a little bit above the line, and that's who we circled right here. And then the largest residual is, if we look here, it looks like the student who weighs 68 pounds, and that's the value right up here. So verify these calculations. For the student who weighs 48 pounds, checked, observed, minus predicted, gives us this residual. And similarly, for the student who weighs 72 pounds, the observed value 7% minus a prediction, 16.5640%, gives us this residual. And then here's line C. So we're going to do similar calculations. We've identified the student closest to the line and the student farthest from the line. You can see here who has the smallest residual. You can see it is this student right here at 54 pounds, a little below the line. And the largest residual is this same student at 68 pounds, who's pretty far out there. You can verify our calculations here. So for the student who weighs 59 pounds, check the observed percent, 7% minus the predicted percent, and you get this error residual value. Do the similar verification for the student who weighs 76 pounds. And then here's line D. It's just the horizontal line through 19.5. And so you see all the predictions here on 19.5, and you can check some of these residuals. So for the student who weighs 62 pounds, we say 18 minus 19.5 is negative 1.5. And for the student who weighs 104 pounds, 26 minus 19.5 is 6.5. And here we've got two students who are furthest away. These are the two students who are negative 12.5, and then there's a third student who's a positive 12.5 residual. And then this student right here is pretty darn close to the line. This is the student who weighs 95 pounds. So now we have to figure out, well, what's the best error? So there's three different ways of analyzing the errors to think about what's the total error for these graphs. So the first calculation is the sum of the errors. So you take all of those residuals for line A in this residual column, the last column over here for each of the lines, and you add up those errors. So that's how we got the sum of the errors for line A, B, C, and D. And you can verify these on a calculator, or you could type them into Excel and let Excel sum them up really quickly for you. Then we want to think about, well, what's the sum of the absolute value? Because we know the sum of the errors, we've got some cancellation going on there. So the absolute value, we convert all of the errors to positive values. That's what absolute value tells us to do. And then we sum them up. So these are larger values because we don't have the positives and negatives canceling each other out. Remember, in statistics, we have another way of converting from negatives to positives, and that's by squaring. So this last column is the sum of squares of errors. So we take each of the errors and square it, so that converts negative errors to positive, and positive errors stay positive, and then we sum it up. So all three different measures of total error are valid ways to analyze errors to see which line has the least error. So here, which line has the least error? Well, if we look at line B, it has the least sum of errors, it has the least sum of absolute value of errors, and it has the least sum of squares of errors. So line B overall is the best fit no matter which error method we're using to try to analyze the total error. The regression line is called the least squares regression line because we typically use the sum of squares of errors method to find the line of best fit. Any of these methods will help us find the same line of best fit, but the sum of squares is a little bit easier on calculation-wise because squaring is a lot quicker for a computer to do than find the absolute value. So that's why our regression line is called least squares regression. That's the method we typically use. So line B is the best fit line because it has the least total error, whether you look at sum of errors, sum of absolute values of errors, or sum of squared errors. And line of best fit always is the least of all of these error methods. So sum of errors, we could say SOE for short, SAE for sum of absolute value of errors, and SSE for sum of squared errors. And there's a note here, statisticians square the errors and then find the line that minimizes the sum of the squares. The line that has the smallest sum is called this least squares regression line. So now we want to think about, is there a pattern in the residuals or not? So if you plot the residuals from our best fit line, we should see a random pattern. So let's go look at our line of best fit that we chose. That was line B here. And we want to plot out these residuals and see how they look. We can pull up this data. I just typed in the observed body weights and backpack percentages. And if we go to stat, regression, simple linear regression, and we choose our x variable to be the body weight and our y variable to be the backpack percent, we can see our line of best fit is going to be a match for line B. And then down here under save, I'm going to say save the residuals. And let's look what happens. So here's our typical results over here, like we're used to seeing. And you can see, give or take rounding, this is a match for line B. And if we come over here and hover our mouse over, we can see that looks just like line B. The window is kind of stretched a little bit different, but you can see the lines going through about where line B went through. And then this column of residuals is saved. Now, if you notice, these values are a little bit different than what we have in our notebook in the activity packet, because these are less, more accurate. They're less rounded. So when we were doing all those calculations, we were rounding along, but to 1 or 2 decimal places, they're the same. So I want to see a scatter plot of the residuals. So I can go into Options, Edit, and then under Graphs, if we scroll down, we can see residuals versus x values. So let's click on that and compute, and now I get a third screen with a graph. And so here's the residuals. So here's our x values, body weight of the students, and then the residuals appear to be random. That's a good thing. And here's 0 going through the middle. So we want to have random residuals to show that the errors don't have any pattern, that they happen by chance, and that tells us the linear model is a good fit. We see roughly about half the errors are positive, about half the errors are negative. That's the kind of relationship we're looking for. So we say here that the residuals appear to be random, so we conclude that the linear model is a strong fit.